Assalamualaikum and hi everyone. I'll be starting off our presentation by introducing our project, EcoSense. I'll walk you through what is the main problem we are trying to solve, who we design EcoSense for, what existing solutions are out there, and how we shape our design based on real user needs. Now let's get into the problem we are addressing. In agriculture, especially in palm oil plantations, chemical fertilizers and pesticides are widely used to boost growth, but when it rains, these chemicals often get washed away into nearby water channels. Over time, this will throw off the pH balance of the water. It might sound like a minor issue, and the effects are serious. When the soil and irrigation water are not in the right pH range, it will result in crop health drops, and for small-scale palm oil plantation owners, even a slight drop in productivity hits hard, especially when they don't have much margin for trial and error. Our solution is designed for a very specific user group, which is new and small-scale palm oil plantation owners. These are individuals who are relatively new to farming, often with limited technical knowledge and resources. They typically manage small plots of land where even minor issues like overwatering, poor soil conditions, or pH imbalance can significantly impact their crop yields and ultimately their income. Talking about our target users, we need to know what are their needs. First, they need a way to track pH levels in real time, so they don't find out too late when the water have already gone bad. Second, they need a way to monitor soil moisture to avoid water waste. And then they need to keep an eye on the temperature trends, especially after spraying fertilizers and pesticides. Finally, they need a system that is simple, affordable, and able to survive on the outdoor condition. To ensure our solution fills the right gaps, we analyze a few existing approaches and tools currently used for monitoring environmental conditions in agriculture. First, we have community-based monitoring. This method involves local volunteers using basic test kits to visually assess water quality while it's low cost and accessible. It's manual and labor intensive, data collection is infrequent and inconsistent, and it relies heavily on the observer's judgment. There's no automation, no continuous tracking, and no historical data storage. Second, we have Horiwala Core Twin pH22. This is a portable digital pH meter that offers much better accuracy. It is designed for spot checks of soil or irrigation water. However, it still falls short in several key areas, which is it only measures pH, offering no insight into moisture or temperature. It's a manual use device, meaning the user has to go to the field, take samples, and interpret the results each time. And then there's no data storage, and it's not designed for long-term unattended operation. It's more advanced than visual kits, but not very scalable or convenient for regular monitoring, especially for smallholders managing busy daily routines. Third, our system, EcoSense. EcoSense was designed to address the limitations of previous method. Here's how it compares. Unlike manual approaches, it offers real-time, automated monitoring of key environmental parameters. It integrates 3 sensors, pH, moisture, and temperature, which is providing a more complete picture of the field conditions. Data is displayed on a built-in LCD, so the user doesn't need additional equipment or apps. It's housed in a weather-resistant casing and powered by a long-lasting battery, making it ideal for outdoor use. It can also support data logging through an optional SD card module, giving farmers access to historical trends when needed. We ensure our design delivers better functionality, automation, and usability, especially for users who need straightforward and actionable feedback in the field. Now let's go over the design specifications for EcoSense. Basically how we translated user needs into actual features and technical goals. We broke it down into 3 categories: must-have, should-have, and could-have features. First, the must-have. These are the core features the system can't function without. We included a pH sensor to monitor water quality in real time. A soil moisture sensor helps avoid over or underwatering with quick response times. We also added a temperature sensor to monitor environmental changes, and all of this data is shown clearly on the LCD display. Next, the should-have. These features make the system more practical for everyday use. We added an SD card module so users can log sensor data for data analysis. A waterproof casing protects the electronics from rain and heat in the field, and to make it low maintenance, it runs on a rechargeable battery. Finally, the could have. These are the optional upgrades that we might include in the future. A high contrast OLED screen could improve readability even more, and wireless connectivity like Wi-Fi or GSM would let users check data remotely from their phone or laptop. Each feature directly responds to what our target users need, especially smallholders who want something simple, reliable and affordable.
Okay, building on what my teammate just explained about the user needs and design goals, especially for rural plantation environments, I will now walk you through the actual prototype we have developed. So here, you can see the complete device. At the heart of it is a rugged, waterproof and weatherproof casing. This was essential based on the user needs, since we are deploying this in a harsh outdoor conditions, especially near palm oil plantation stream water. On the front, we have integrated an I2C LCD screen that display all three key environmental parameters in real time: pH, temperature, and soil moisture. This allows any farmer or worker to instantly read water and soil health on the spot. In addition to real-time display, we have also added an SD card module inside the enclosure for data logging. So even without the internet or mobile apps, user can still track environmental trends over time by reviewing the stored data. And for simplicity and portability, the device is powered using a basic USB power bank, making it highly deployable even in off-grid plantation sites without electricity. This design directly fulfills the earlier design criteria of being rugged, standalone, low cost, and practical for new farmers in rural areas. Now, let's break down the system architecture based on our circuit diagram. At the core is the Arduino Uno, which serves as the brain of the device. It receives input from the three key sensors. The pH sensor measure the water acidity or alkalinity, vital for understanding runoff water impact on crops. The DS18B20 temperature sensor reads environmental or stream temperature. We included a 4.7K ohm pull-up resistor between the data and VCC lines. This is important for accurate digital temperature readings. The capacitive soil moisture sensor monitors soil saturation near the drain. We choose the capacitive type specifically because it's more durable and less corrosive than resistive type, aligning with long-term outdoor use. All sensor readings are displayed in real time via the I2C LCD, which helps reduce wiring complexity, an important consideration for prototyping and maintenance. So every reading is also logged to the SD card in CSV format with timestamp, so user can insert the card into a laptop later and check changes over a days or week. They also can use Excel. So powering the entire system is a USB power bank, which is widely accessible and rechargeable. This decision meets our energy constraint target and user needs for low maintenance, portable operation. So from a technical standpoint, the device integrates both sensor, functionality, and data collection in a way that supports the user, workflow, and survive tough plantation conditions.
Hello, my name is Ibat Harzan bin Hasri, and now I will be talking about our validation plan where we run tests and set up calibrations to ensure that every component in our prototype works perfectly. First of all, we will test the pH sensor. First, we test with a pH solution with the value of 7. And as you can see, it gives a reading close to 7. Next, we test with a pH value of 5. The results deviate at most only by 0.2. Lastly, with a pH solution with a value of 9. And like before, it gives a value reading close to 9. Next, we will test the temperature sensor. We collected both hot and cold water from the water dispenser, as it had a fixed value of 60 degrees Celsius for hot water and 70 degrees Celsius for cold water. First, we test using the warm water. And as you can see, it gives a reading close to 60 degrees. Next is the cold water. and it gives a reading close to 17 degrees Celsius. Next, we will test the soil moisture sensor. We will test the moisture percentage of the soil on 2 different days. First, on a very rainy day, and second, on a very sunny day. On a rainy day, it gives a moisture percentage of around 80%, while on a very sunny day, it gives a percentage of around 10%. The reading showing a high moisture percentage on a rainy day and a low moisture percentage on a sunny day shows that the sensor is working perfectly. Next, we will test the weatherproofness of our casing. This is to ensure that all the electric components won't get damaged during heavy weather. We will douse the casing under running water. And as you can see, the interior of the casing is still completely dry. Now, I will summarize our value proposition and with that, conclude the entire presentation of our project. In many smallholder plantations, it's difficult to keep track of how fertilizers and pesticides affect the environment. Often, water pollution or soil degradation only becomes obvious after damage has already been done, like fish dying in irrigation channels or crop performance declining. Our solution is a low-cost, field-ready device that monitors water pH levels, soil moisture percentage, and water temperature in real time. It logs data every 4 hours onto an SD card, graphs the result on an Excel sheet, runs on a rechargeable power bank, and is designed to be easy to install and maintain even without technical expertise. With this tool, plantation managers can detect abnormal pH levels early on, long before they lead to fines or environmental issues. They can also track conditions after fertilizer use to optimize timing and avoid over-application. The main value we offer is prevention and precision, helping smallholders stay compliant with regulations, protect the environment, and make informed decisions about fertilizer use. Ultimately, this device empowers farmers with the data they need, simply and affordably, to manage their plantation more sustainably. On behalf of all my group mates, thank you very much for listening. Assalamualaikum warahmatullahi taala wabarakatuh.